only works on primary amides, because we need to have two acidic hydrogens on our nitrogen. The pKa of the CH2 adjacent to the amide is actually around 30. It's significantly less acidic than the pKa of an ordinary ketone. It is kind of on the order of 20 to 22. And that's because you've got the carbonyl group being stabilized by a significant contribution from this minor resonance structure. And to the extent that the carbonyl group is stabilized by that minor resonance structure from donation of the lone pair on nitrogen, it doesn't need to be stabilized by taking an adjacent hydrogen off. One of the things that makes those protons acidic is the contribution from the resonance structure that puts a positive charge on the adjacent carbon. Hydrogens adjacent to a positively charged carbon tend to be quite acidic, but this isn't as positively charged in the amide case. But what that does do is dramatically decrease the pKa of the hydrogen attached to nitrogen. An amine hydrogen has a pKa of about 35, but this amide hydrogen has a pKa of around 16. What that means is you are not going to deprotonate the carbon of a primary amide. You can deprotonate the carbon of a tertiary amide, so it's possible to treat this with really strong base and take off one of these protons because there are no hydrogens on the nitrogen to remove. But if there are hydrogens on the nitrogen, there's a huge difference in pKa between the hydrogens on the nitrogen and the hydrogens on the carbon, and you're only ever going to take off the hydrogens on the nitrogen. And it takes a really strong base to do this, too. To make the enolate of a tertiary amine, because the pKa is 30, right? So you need a base that's stronger than that. So it would take something like sodium hydride or an alkyl lithium reagent itself to do that. Yeah. But because this is a pKa of 16, 16 is not a particularly acidic or a particularly weak acid. It's comparable to water, in fact. So just plain old hydroxide ion is basic enough to pull that hydrogen off. And I'm showing it from the minor resonance structure, but you could also show it from the major resonance structure of the amide. Three arrows take the hydrogen off, push this pair of electrons into form the pi bond, and then push the pair of electrons out onto oxygen. So the effect will be to form the nitrogen analog of an enolate. It's not an enolate ion because it isn't a carbon-carbon double bond, so it's not an alkene, but it's functionally equivalent. And it's got a resonance structure. It has a negative charge on the nitrogen. Try to be consistent and have 6 carbons in all my intermediates, but feel free to let me know when I screw that up. So just as in the Huntsbeker reaction, we have the oxygen anion, the carboxylate salt, doing a SN2 displacement on bromine. This nitrogen anion can do the SN2 displacement on bromine, end up making a nitrogen-bromine bond. And you can show it from either of the two resonance structures. Once your arrows match what you're doing, and the product will be a new nitrogen-bromine bond. Right, so it's pretty simple. It's just a two-step reaction. One, deprotonate.
Are they both irreversible?
And two, bromate. The first reaction is not and has a K2 of about 1.
Oh, okay.
Ish, right? Because the pKa of water and the pKa of this nitrogen-hydrogen
Right.
bond are about the same. The second step is effectively irreversible. Bromide is not likely to come back in and take that out.
Oh, thank you.
So two steps, deprotonate and then brominate. Very much like the first two steps of the Huntsbeker reaction, where we deprotonated and then we brominated to form the hypobromide. Is this hydrogen more or less acidic than the hydrogen in the initial candidate? It also has a resonance structure,
More.
of course, right? More acidic. Why do you say this is more acidic?
Well, it has the positive charge on the nitrogen in the resonance structure. But my initial
That one did too.
thought is that bromine is electron withdrawing. And it's a terrible base.
That's the key. The bromine is electron withdrawing. It's pulling electron density away from that nitrogen and making it even more positive than it was on the initial material. Which means that this hydrogen is going to be removed pretty readily. And that's got a resonance structure. Right, so that's just another acid phase reaction. And now shit gets weird. What you might predict by analogous to previous reactions is that that nitrogen anion would now attack another molecule of bromine. You put a second bromine on the nitrogen. That's what would happen if it were carbon. But it isn't carbon, it's nitrogen. And so what happens is that compound the negative charge of the nitrogen. Nitrogen says to bromine, dude, I hate this being negative crap. I'm not a very electronegative element. I'm having trouble stabilizing this negative charge. Well, why don't you just leave and take those damn electrons with you? And so bromide just falls off as bromide. It leaves you with a weird-ass nitrogen that's neutral, that has an unfilled octet. This is called a nitrene. And it's analogous to carbines. where the same element has a lone pair and an unfilled octet. But no formal charge. So it's neutral nitrogen. It's got 5 electrons, which is the valence of nitrogen. That's what it brought. But it's really unhappy because it has an unfilled octet. And it also has a lone pair. Nitrene is the key intermediate. Instead of brominating again to form 2 nitrogen bromine bonds, bromide atoms weakens. As you might imagine, the nitrene is pretty unstable. Right? It's not very happy at all. There's a resonance structure for this nitrene. It looks like this. What's going to happen now is there's going to be a shift. This alkyl group is going to walk over onto the nitrogen and form a carbon-nitrogen double bond. And you could actually do it from this resonance structure as well.
Would that nitrogen have a positive charge on it?
This nitrogen, sorry, yes. Right. So you can do it from either resonance structure, but it's an alkyl shift. The alkyl group moving on the nitrogen and a carbon-nitrogen double bond forming. To make an isocyanate. Actually, what I want to do is number these carbons. So the carbon that was the carboxylic acid, carbon 1, is now actually between the nitrogen and the oxygen, and you formed a new bond between carbon 2 and the nitrogen. Isocyanates are very reactive. They will react with base. Remember the base? There was still base present. This is irreversible, right? It's an alkyl shift. It's an alkyl shift that's driven by being pushed by a negative charge rather than being pulled by a positive charge like the alkyl shift you saw in carbocation rearrangements. So this alkyl shift is more analogous to the alkyl shift that you see in the oxidation step of hydrochloration, where you get a negative charge pushing that alkyl group over. Hydroxide can now attack the carbonyl. And because that carbon has 2 electronegative elements pulling electron density away, it's quite positive. Got a significant partial positive charge on it. And it'll look like that, but it also has a resonance structure that puts the negative charge on the nitrogen. And that'll get protonated by water. Which you can show from either resonance structure. And this makes a carbamic acid. It's a carbonyl group that's between an NH and an OH in this case. So it's got an NH on one side and an OH on the other side. That's a carbamic acid. Those are unstable and they spontaneously rearrange. Do a transition state. That's a 4-member ring. liberated CO2 gas and form that new NH bond. There's a 4-member ring transition phase to it. The nitrogen is essentially deprotonating itself. Carbamic acid. That carbamic acid is pretty acidic because you've got the electron withdrawing nitrogen pulling electron density away from the carbonyl. So there's 3 key intermediates in the Hoffman rearrangement. There's the nitrene, which is that unsaturated nitrogen, neutral formal charge, both with an unfilled octet and lone pairs. There's the isocyanate, which is that NCO bond, which happens after the alkyl shift. And then there's the carbamic acid, which is what happens when the isocyanate gets attacked by base, and then that negatively charged intermediate gets protonated. So it's a bunch of steps. First, starting with a bromination on nitrogen, then an acid-base reaction, right, which is step 3. This is step 4, the loss of the bromine, right? Because we have the acid-base reaction, then we have bromination, then we have another acid-base reaction. Step 4, the nitrene rearrangement, that's the key step, that's step 5. In step 6, we have the base attacking. In step 7, we have the protonation to form the carbamic acid. And then our last step is the loss of the CO2. So if you remember what the key intermediates are, that you have a nitrene, you have an isocyanate, you have a carbamic acid, that will help you make sure you don't skip steps. And the product, right? Carbon 1 is this one that's got lost as CO2, and we have a amine that's got 1 fewer carbons than it used to have. Has to be a primary amide, because if there's not a primary amide, there's not a second hydrogen to take off to generate this material, right? So the reaction that led to that was deprotonation of this second hydrogen. And you can't do that if it wasn't the primary amide. If it was a secondary amide, you'd be stuck here, right? There'd be an alkyl group, and you'd have this bromine, and you're done. If it's a tertiary amide, you can't even brominate it in the first place. The hydrogen that's going to be removed in the tertiary amide is actually the one with the carbon. So that's the Hoffman rearrangement. Let's take our break, and then we'll have about half an hour, and we'll come back and do the helpful electrolytic reactions. And then we'll be done with reactions, and you have a whole week to cram for the exam. No cramming, right? Because you've been keeping up.